Hey guys, after looking at yesterday's notes from the sub, I realized that for some of you who are learning about equilibrium for the very first time, this may have been a little bit more difficult than I intended, so I figured I'd make a quick video, share it out, and see if that can help some more people get started with this whole topic. Before I go too far and say too much, just remember to make sure and read these little paragraphs entitled Why. A lot of times the answers to the questions that you don't know can be found within these words, so if you just quickly kind of breeze through, you're likely to find whatever is missing. So that being said, let's take a look at Model 1, which simply introduces to you the idea of a reversible reaction. If you've never learned about this before, this is simply there to tell you that there are some reactions that go both directions. So not only does A turn into B, B is also turning back into A simultaneously. We would still call A the reactant, we would still call B the product, but technically the reaction is going both ways. Whenever you see the double arrow like this, that arrow is indicating to you that this is the type of reaction that occurs in both directions simultaneously. The next part that I thought might be kind of tricky is question 6, which starts to tie some values, some quantities into the whole mix here. Using the same reaction, A turning into B, the question says, what if you had 5 moles of A and 0 moles of B initially, but you knew that 60% of the A molecules reacted each minute, and it asks you to calculate the quantities at the end of that first minute. The first thing you need to do is be able to find 60% of those 5 moles. I assumed most people could do this, but if you're not quite sure, simply take the 5 moles times 0.6. This tells you 3 moles of A reacted. That 3 moles gets filled in for the amount of change. You started with 5 moles, we reacted away 3, so you're losing 3 of the 5. This also tells you that B is going to gain by 3 moles. How did I know that? If you go take a look back at the equation, because it's 1 to 1, every 1 mole of A will give you 1 mole of B. So every 3 moles of A will produce 3 moles of B. So as soon as I know I lose 3 moles of A, I must also gain 3 moles of B. This lets you calculate the final amount of moles. 5 minus 3 is 2 moles of A left after the first minute, and 3 moles of A have been formed after the first minute. Then we move down to question 8, which adds an extra level of complication, taking into account that not only is A turning into B, B is also turning back into A. So I have the same 60% of A filled in, minus 3 moles of A, which is going to produce 3 moles of B. But then we have the added complication of 20% of the available B molecules react each minute. So starting with 2 moles of B, 20% of those is going to react. 20% of 2 is 0.4. So we're also losing 0.4 moles of B in that same minute. Because it's a 1 to 1 ratio, if we lose 0.4 moles of B, we're going to gain 0.4 moles of A. Taking all these changes into account, the 2 moles plus the 3 minus the 0.4, at the end there's 4.6 moles of B remaining. Same thing on the A side, 2.4 moles of A remaining. This is the kind of math you have to factor in for a reaction that goes in both directions. And lastly, let's take a look at Model 2. This is where I'm thinking most of you probably thought you couldn't go any further, especially because A and B don't have initial concentrations, so you may have not known what to do there. To make this as simple as possible, let's just start off with A and B having the same number of moles as the previous example. So for A, let's assume initial amounts of 5 moles. And for B, let's assume initial amounts of 2 moles. The reason we'll start with 5 moles and 2 moles is because that lets us use the same numbers as the previous example, so we don't have to do any extra work for this first step. So we end up with the same 2.4 of A, 4.6 of B. The difference in Model 2 is it's going to ask you to do those same calculations over each minute. Now it's not labeled with the percentages, but they intend you to use the same 60% of A reacting and the same 20% of B reacting over each consecutive minute. And if you do this, you'll eventually see how this very special point known as equilibrium is established. So if you're still not quite sure how this works, let me do just this 2-minute example with you, so you can see how the whole thing goes. So after the first minute, we have 2.4 moles of A. 60% of that is going to react. So find 60% of 2.4 that ends up being 1.44. So that's how much A we're going to lose because of the 1-to-1 ratio. That's also how much B we're going to gain. So it's the same amount for both. After the first minute, we had 4.6 moles of B. The same 20% of that is going to react. So find 20% of 4.6. That is 0.92. I'm going to round each of these to 2 decimals the whole way down just to be consistent. We're going to lose 0.92 moles of B. That also means we're going to gain the same 0.92 moles of A. If you follow all this math through, 2.4 minus 1.44 plus an extra 0.92, you get an end concentration of 1.88. And on the other side, you started with 4.6, you gained 1.44, but you also lost 0.92. You get a final concentration of 5.12 after the second minute. And you go ahead and do this same math for 3 minutes and 4, and eventually it'll become really obvious to you what equilibrium actually is. And that pretty much sums up everything I wanted to say about this introductory equilibrium packet. You'll be on your own for the rest of it. If you do have any questions, just try and keep them in the back of your mind, and we'll talk about them the following day.